Hello students, this is Bappaditya Chakravarti and you are watching our YouTube channel Chemistry for NEET. Now today's topic is thermodynamics. To start with, what is thermodynamics? Where from the name came? Thermodynamics means dynamicity of heat. This is basically a chapter of physics where we learn about flow of heat, etc., etc. But in chemistry, thermodynamics is also very important chapter, as each reaction, each chemical reaction, there must be some absorption or elimination of heat. Either a reaction is endothermic in nature, where the heat is absorbed, or the reaction is exothermic in nature, where the heat is released. Now for a particular reaction, whether the reaction will release some heat or it will absorb some heat, how can we say? That's the reason we learn thermodynamics in chemistry also. To start thermodynamics, we need to know some terms. First of all, what is a system? What is a system? System is a part of universe separated from the universe by a boundary wall and taken for observation. Now, if you take a test tube where some chemical reaction is going on and you are observing the reaction, the changes occurring in the reaction. So here the system, to you the system is that reaction. Okay, now that reaction or the reagents taken. Now the reagents or the solution or the chemicals are taken into test tube. So it is a system and it is separated from the universe or separated from the surroundings by boundary walls. Here the boundary walls is the glass, that is the wall of the test tube. Now systems are of three types. Number one, an open system. Now what is an open system? Open system is that where both the mass and the energy are exchangeable with the surroundings. If you take a cup of hot tea, then the heat is emitted to the surroundings and some amount of tea is here can be again entered or can be taken out from the cup. So this is an open system where both mass and energy are exchangeable with the surroundings. Next, number two is a closed system. Now what is a closed system? A closed system is that a sealed bottle, like a sealed bottle of a cold drink, where mass cannot be taken out from the system. That is, exchange of mass is not possible. But if you take if you keep a bottle of sealed cold drink in open air, then the heat can be entered into the bottle. Therefore the exchange of energy is possible with the surroundings but not the mass. So in open system both mass and energy are exchangeable with the surroundings, but in an open system not mass but the energy is exchangeable with the surroundings. Number three is isolated system. Isolated system. Now in an isolated system, neither mass nor the energy is exchangeable with the surroundings. Okay, if a reaction is or if some hot water is kept into a thermoflask, then that remains hot for some times. That means energy is not exchangeable with the surroundings and mass, of course, mass is not exchangeable. Therefore in an open system both mass and energy can be exchanged with the surroundings. In a closed system, not mass but energy can be exchanged with the surroundings. And in an isolated system, the example is a thermoflask. Isolated system, the example is a thermoflask where neither the mass nor the energy can be exchanged with the surroundings. Okay, so these are the systems. Now systems are separated from the universe by boundary walls, and we have said earlier what boundary walls are of two types: diathermal, where exchange of energy is possible, and adiabatic, where exchange of energy or heat cannot be possible. Those two are the boundary walls. Next, the functions. If you want to define a system in chemistry, systems are like a cylinder of gas or a reaction medium where some reaction is going on. So in case of a gas taken in a cylinder, to define the state of the gas, the functions or the properties we need to say are the pressure, the volume, the temperature, and the number of moles. These are the fundamental functions or the fundamental properties of a system. To define a system, these properties are very necessary. Okay, other than those four properties, we cannot define a system. There are some other properties also which are called thermodynamical properties, and we will know this about this in this chapter. Those thermodynamical properties may be the heat change, maybe the internal energy, maybe the enthalpy, maybe the work done by the system or work done on the system, maybe the entropy, etc., etc. These are called the thermodynamical or thermodynamic functions or thermodynamic properties. Now these properties are divided into two categories. These functions are divided into two categories: state function and path functions. What is state function? State function is that those properties or functions which do not depend upon the path of the change. When a system, say a cylinder of gas which was taken in a cylinder with a frictionless piston, a gas is taken in a cylinder with a frictionless piston. The piston can't go upward and downward without friction with the wall of the container, and inside this some amount of gas is taken. And to define the state of the gas, the necessary fundamental properties or functions are P1, pressure is P1, volume is V1, and temperature is T1. Okay, now if some amount of heat is given to the system, okay, if some amount of heat is given to the system, then system will absorb that heat. The energy of the gas molecules will be increasing. The gas molecules will translate with faster speed. They collide with each other, and they also collide with the wall of the piston, and therefore the gas will expand and the piston will go upward. Okay, if this is the final condition or final position of the piston, then the volume increases, that V1. So pressure will decrease and will be decreasing, and volume will be increased. So the pressure is P2 in this state, pressure is P2, volume is V2, and if this no temperature change occurs, then temperature will remain constant, and that type of change is called isothermal change. Okay, so in case of isothermal change, temperature doesn't change, so the system go from one state to another state. If that occurs it may occur in two different pathway. Number one, reversible pathway, and number two, irreversible pathway. Now what is a reversible change and what is an irreversible change? Okay, so a reversible change is the change which occurs in infinitesimally small steps. The overall change, like here the pressure is P1, volume is V1, and temperature is T1, and here the pressure is P2, volume is V2, and temperature is T1. So the overall change is divided into infinitesimally small steps, like here P1, and in that state this one is P1 minus dP1, volume is V1 plus dV1, etc., etc., and here P1 minus dP2, etc. So each step is reversible with respect to the other. Each step is reversible with respect to the other. That is why the overall change is reversible. And in case of an irreversible change, the overall change occurs in a sudden way and with an external, against an external pressure, or external pressure means here pressure remains constant. Okay, so the overall change here, volume is pressure is P1, volume is V1, and here volume is V2. So the overall change is V2 minus V1 against the pressure P. P remains constant and volume changes from V1 to V2, and that change occurs all of a sudden, and that kind of change is called irreversible change. Okay, so we can compress the piston on a sudden, at a sudden, with an external pressure of P, or we can change the position of the piston through divided into small steps, like small steps. Total change is divided into small steps. That type of change is called reversible step. Now, if any thermodynamical property like enthalpy or work done or entropy or internal energy change, if it doesn't depend upon the way of the change, that is whether it is irreversible change or reversible change, if the internal energy remains same, whether the change occurs in irreversibly or irreversibly, if any thermodynamic function remains same, then that function is called a state function. Okay, so a state function is that which doesn't depend upon the way of the change, and a path function is that which depends upon the path. Like we'll see later that work done is such a thermodynamical property. If it occurs in reversibly, then the expression of work done will be different when it occurs in reversible way. Okay, reversibly expression of work done is different, and in irreversible way expression of work done is different. So work done is such a thermodynamical function which depends upon the way of change, upon the path of the change. That is why work done is called a path function. But internal energy change, that remains same whether the change occurs in reversibly or irreversibly. That is why internal energy change is called a state function. Now, what is internal energy? Actually, we take food from outside, and then the food is through the process of respiration, it is oxidized into glucose, and some amount of energy is released, and with that amount of energy, we do some work. And if we do not do any work, then food is not necessary for me. Food is also necessary whether we do or do nothing, but food is necessary to maintain the different metabolic work inside our body. So this is called the internal energy. Our internal energy composed of different way, like our heart is pumping, that requires some energy. Our brain is working, that requires some energy. The blood is flowing through our body, that requires some energy. Everything to maintain this body, energy is required, and that energy we take from outside in form of foods. So by the other form, and the rest amount of energy we use to do some work. So the total amount of energy we gathered from outside in form of food, that total amount of energy is divided into two parts. By the one part we increase our internal energy, and by the rest amount we do some work, and that work may be mechanical work or non-mechanical work. Non-mechanical work where force, mechanical work is measured by the force and displacement, But now what I'm doing, I'm just talking with you, so this is not any kind of mechanical work done, but still I'm working. So this kind of work is called non-mechanical work done. So the total work done is of two categories: mechanical work done and non-mechanical work done. Let's come to the point. The total amount of energy absorbed by us is used in two different way. Number one, to increase our internal energy, and number two, the rest amount we do some work. Similarly, if some amount of heat is given to a system, that is in a cylinder of gas with a frictionless piston, if it is given to the system, the piston go upward. So this is a mechanical work that is done by the system. System is doing some work, but the amount of work done, we can measure the amount of work done, and we also can measure the amount of heat given to the system. These two are not exactly equal. Okay, the amount of heat given to a system is always greater than the amount of work done by the system. So where goes the rest amount? The rest amount actually increases the internal energy of the system. Now, what is the internal energy of a system? Here the system is a cylinder of gas. So in case of a gas molecules, their internal energy may be considered as their translational energy. So after absorbing the energy, their translation energy will increase. The molecules will start to translate more rapidly. Their rotational energy may be increased. The molecules will start to rotate. Their vibrational energy may be increased. The molecules start to vibrate through the bonds, etc. So there are so many types of internal energy. We cannot actually calculate the absolute value of the internal energy of a system. So absolute internal energy of a system has not any absolute value, or rather we cannot calculate the absolute value of an internal energy of a system. But if some amount of energy is given to a system, and if system done some work, then the rest amount, that is if dq amount of heat is given to a system and dw of work is done by the system, then the rest amount, that is dq minus d, that will be dq minus dw. dw is the work done by the system and dq is the amount of heat given to a system. Okay, if dq amount of heat is given to a system and the system do some work, like dw amount of work is done by the system, then the rest amount, where goes the rest amount? Actually increases the internal energy. So the rest will be the internal energy change of the system. So we can write this equation: dq plus dq, here internal, here dq amount of heat is given to a system and system do some work like dw, therefore dq minus dw will be d, or we can also write dq minus d equals to dw, or we can also write dq equals to d plus dw. Okay, dq equals to d plus dw, and that is the expression, that is the mathematical expression for first law of thermodynamics. Now dq is the amount of energy, heat energy, that is it's an amount of energy. D is the internal energy, so it's also energy, and dw is work done, that is also a form of energy, the unit of work done. You know what energy of work done is just same as the unit of energy. So w, or work done, is also a form of energy. So this is the sum of energy, and this is the energy given to a system, and this is the amount of energy how the system used up that amount of energy. So we can say energy cannot be neither be created nor be destroyed. If some amount of energy disappeared, then the equivalent amount of energy must be appeared. Okay, so the first law of thermodynamics is just same as the law of conservation of energy, which states that, so if you need to state the first law of thermodynamics, you just write that the first law of thermodynamics is that energy neither be created nor be destroyed. If some amount of energy disappear, then equivalent amount of other form of energy must be appeared. That is the statement of first law of thermodynamics, and this is the mathematical expression of first law of thermodynamics. Okay, so that's all for the today's video, and the next day we will continue thermodynamics.